Hi everyone, today we're going to learn about exponential functions and graph transformations. So let's get started. First, we're going to start with a warm-up, and this warm-up I am asking you to find the inverse of this function. So there's a couple of steps that you need to do in order to find the inverse. So f of x is actually, we're just going to replace that with y because f of x equals y. F of x just ensures that your equation is a function. So you have 2x minus 4 all over x plus 5. Now, the first thing you do when you are looking to find an inverse is that you switch your x and your y. And then the second thing that you're going to do is solve for y. So number one, we are going to exchange your x and your y value, your x and your y variables. And number two, we're going to solve for y. Okay, so when we do that, okay, that's going to give us the inverse. So switching the x and the y, we have now x is equal to 2y minus 4 over y plus 5. So now that I've switched my x and my y, now I need to solve for y. The way you're going to solve for y is you're going to cross multiply. So now we have x times y plus 5 is equal to 1 times 2y minus 4. I'm going to distribute, so I have xy plus 5x equals 2y minus 4. I realize that I have x's on both sides of the equation, so I am going to bring this 2y over. So I have xy minus 2y. I'm going to move this 5x over to the other side. So I have negative 5x minus 4. I'm going to factor out a y. So now I have y times x minus 2 is equal to negative 5x minus 4. And finally, y equals negative 5x minus 4 divided by x minus 2. And this allows us to put this little inverse there because that becomes my inverse of the above mentioned equation. A couple of things. Let's graph this and see what it actually looks like. In graphing this right here, you have, let's start off with our vertical asymptotes, which is x plus 5. So now we're going to plot negative 5, which is right here. So there's my graph, my equation. I notice for my horizontal asymptotes, I look at these two equations from here. And if you've missed the whole asymptote, horizontal and vertical asymptotes, and you should look at previous lessons because we've gone over that before. But just to recap really quickly, if my variables have the same exponential power here, then my horizontal asymptote is 2 over 1. So that's going to be up 2 right there. So I'm going to draw in my horizontal asymptote. Now to graph this, usually my parent graph is upright and then down left. However, I just want to make sure by two things. Number one, I'm going to plot my y-intercept. So my y-intercept is when I set x equal to 0. So that's gone. I have negative 4/5. So 0, negative 4/5. And my x-intercept is found when I set the numerator equal to 0. So then you have 2x equals 4, x equals 2. So at 2, I have another value. So to me, it does look like my graph is doing this, which then means this side will do this. Now, keep in mind, they don't actually come together like this or go down like this unless you have a multiplicity of 2, meaning unless this maybe is squared or something like, or the number on top, either one. And so what happens here is that because we don't have a double multiplicity, then these graphs aren't coming together like that. The second part of this equation, which I know you can't see because it's rolled down a little bit, but it does say give the domain and range of each. So if this is my graph for my f of x, then my domain of my graph for this equation, for my f of x equation, is going to be negative infinity to this value, which is negative 5. So you'd be negative, it's because it goes left to right. And when you have a break in your graph, when you're going this way to the right, you stop here at negative 5. So you have negative infinity to negative 5. Also, it's a union because you have two parts of the graph. So the second part of the graph is going to be negative 5 to infinity. Now, my range is always going to be low to high. So that's going to be low value, which is this keeps going down. And then when does that get high? Well, it stops here at 2 because I do have an asymptote there. So it's going to be negative infinity to 2 union, because then it picks back up again and then it goes up. So then it'll be 2 to infinity. And remember, you have to use parentheses because those are asymptotes, and you're not including your asymptotes in your graph. Now, I also need to find the domain and range for my inverse equation, but keep in mind that remember, whenever you find an inverse, the domain and the range is switched. And so the domain of my inverse equation is actually my range of my f of x equation. And so for this, you would say my domain is going to be my range. So that's going to be negative infinity to 2 union 2 to infinity. And my range is going to be my domain. So that's going to be negative infinity to negative 5 union negative 5 to infinity. Now, I always think it's a great idea to graph. And so let's just do a really quick little graph of our equation. And keep in mind, remember, an inverse is always a reflection across your y equals x axis. So our graph is going to look like as if it was reflected across that axis. So let's see what that might look like. We have an asymptote, a vertical asymptote at 2, and that's because of this right here. We have a y-intercept. If I set x equal to 0, my y-intercept is negative 4 divided by negative 2, which is 2. We have a horizontal asymptote, if these are the same. So I do have a horizontal asymptote at negative 5. So that does go down this way. And so that goes down. I do have an x-intercept when I set my numerator equal to 0. So let's see what that would be. Negative 5x minus 4 is 0. 5x equals 4, or negative 5x. So x is equal to negative 4/5. So at negative 4/5, looks like I have a graph there. So this pretty much reminds me that my graph is doing this, and on this end is going to go down like that. So that's my inverse. And so keep in mind, remember, my inverse is across my y equals x axis, and that should look like the same thing as that, or the reflection anyways of that. So the next question that we're going to review is solving, well, actually, these are already inverses, but I want to prove it. And you have to prove it based on what we call composition of functions. So what that means is I'm going to plug in this equation into that x. And then just to prove it again, because you have to see what happens is you have to do it twice. You have to say, you're going to plug in the inverse equation, which is f inverse, into the f of x. You also have to plug in, for f inverse, you have to plug in the f of x equation into that. And if you do that and you get x both times, then therefore, that means therefore those 3 little dots, therefore they are inverses. And so in order to show that, you have to prove it. So you're going to have to plug those into the equation. So let's do that. So for my f of x equation, there it is right there, I'm going to plug this into that. So in doing that, I'm going to go 4 times x. Well, x is now 1/2 x minus 7/4. Let's see here, 4x, and then add 7 all over 2. Okay, so let's do some simplifying here. 4 times 1/2 is 2x. And then 4 times that, remember the 4 is over 1. 4 times that is going to be minus 7. And then I have plus 7, and this is all over 2. The minus 7 and plus 7 do cancel, and I end up getting 2x over 2, which is just x, which is what we wanted. So far, we're halfway done, and we see that that that's an inverse by just putting in your composition of functions. Secondly, now this says to plug the f of x equation, which is this right here, into the x of the inverse, which means now that's going in here. So let's do that. So we have 1/2 times x. Well, x is now, parenthesis, 4x plus 7 over 2. And then now I've got to go minus 7/4. And that's it. It's not all over anything. It's just that. So I'm going to distribute my 1/2. And what that means is this 1/2, 1/2, that's going to multiply. So you're going to end up with 4x plus 7 over 4 minus 7/4. Now, if my denominators are the same, then I can actually combine those under one denominator. So I have 4x plus 7 minus 7 over 4. Well, 7 minus 7 is 0. And what I end up getting is 4x divided by 4, which is x. Again, that's exactly what we want. So all is good. Okay. Now, we're going to start talking about exponential functions and what is an exponential function. I would say the best definition of an exponential function is any equation of a number, and it's to a variable, your x power. Exponential functions always have an exponent of x. That right there, that's going to make your equation exponential. Okay. Couple of things. This value right here, the a, that's actually my y-intercept. So whatever my value is, let's say I have y equals 1 times 2 to the x power. So my y-intercept would be 0, 1. Okay, this value right here is my y-intercept. So 0, whatever that number is. Now, if you notice here, there's the 2 is not my y-intercept. That's my b, my growth or decay, depending if it's a whole number or fraction. But when I was talking about the a, I'm talking about this 1 that's in front of the 2 that you actually don't see, but you know is there. So that's what that does. Okay. In addition to doing this, a function whose value of a constant raised to the power of the argument, basically where e is the constant. Anyway, we're going to be talking about the letter e in just a little bit. So let's look at some more information on an exponential function. When you think of an exponential function, I'm hoping that you're thinking that it does increase rapidly. A couple of things. The base must be positive. You can't have a negative base, or it would be imaginary numbers. So this base, the base being b, always is going to be a positive value. This is always going to be a growth, and the growth is going to be between 1 and infinity, meaning you're always going to have a value that goes from 1 up, but also decay is going to be from 0 to 1. So meaning decay means that if this value here, this b value, let's say wasn't a whole number, and let's say it's a fraction, like 1/2 to the x power. Well, what that's going to do is instead of it being a growth, it's actually going to be a decay. All right, you still have y equals 0 as your asymptote because your growth or decay is going to be above 0. It's still a fraction above 0. So asking yourself, which ones of these are actual exponential functions? So again, it's anything that has a variable as your exponent. So that would be a yes. And remember, my y-intercept would be 0, 1, based on the 1 in front of the 3, like this, 1 times 3 to the x power. For this one, this also would be exponential. And again, my y-intercept would be 0, 2. Because remember, that value right here is my a value. Not exponential because even though this has a power, it doesn't have a power that's a variable. So it has to be an x. This one, again, no, because pi is actually 3.14, etc. And that's not an x. That's still a number. This would be yes for exponential. And my y-intercept would be 0, 1. This is my y-intercept. And this one also would be exponential because my x is in my exponential. It is a power. So in order to start graphing some exponential equations, we're going to start with this one right here, which says y equals 2 to the x power. I'd like you to graph this by hand. I know your calculator does this. Also, Desmos is really great with graphing exponential equations. I'd like to start with 0 and 1. Those are my favorite values to start with. Know that if this value is x up here, usually I put the x values here. If I end up getting something that looks like this and my y is my exponent, I will plug in those values for y first, okay? So when I plug in 0, I'm going to get 2 to the 0 power, which is 1. When I plug in 1, I'm going to get 2 to the 1 power, which is 2. So just based on those two values, I have 0, 1 and 1, 2. Okay, so right now, that may not be enough information to plot, to actually graph my equation, and since that let's say I didn't know what an exponential equation actually looked like. So we're going to plot some more points. So like maybe -2, -1, and maybe a +2. So when I plug in 2 and I say that's to the -2, a couple of things happen. Number one, you do need to remember what a negative exponent does. That will flip my equation and put this 2, which is this 2 right here. That's that 2 right there. And when I flip this over and take the inverse of that, that -2 now becomes a +2. So really, I have 1/4. So at -2, I have, what do I have? 1/4. And then if I plug in -1, now I'm going to go 2 to the -1 power. Again, that's 1/2 to the +1, which is 1/2. And then for +2, I'm going to go 2 to the +2 power, and that's 2 times 2, which is 4. So I'm going to plot all these points. So I already plotted this one here and this one here. So now I have -2, 1/4. So -2, 1/4. And then I have -1, 1/2. And then I have 2, 4. Okay, so basically what I'm seeing is this. Oops, missed it. Okay, so that is an exponential equation. It does go up very quickly. The curve does get closer and closer to the x-axis on the left side right here, but it will never touch because actually what you have, if you have an asymptote at y equals 0, okay? So let's try plotting this one, which is a little bit different. This is 1/2 to the x power. Now, again, we talked about this remember with our y equals a times b to the x power. If this value b right here is a positive whole number, that means my graph is a growth, so it's going to go up. But if this value is a fraction, which basically means it's less than 1, but greater than 0, it's going to be a decay, which means that my graph should go down instead. So let's graph this and see exactly what it does. And again, I'm going to plot 0 and 1 first. I do have an x as my power, so I'm going to plug those values in here. Anything 1/2 to the 0 power is always 1. And plugging in 1, I get 1/2 to the 1 power is still 1/2. So at 0, 1, I'm here, and over 1, 1/2, I'm right here. Now, that is giving me a great, an idea that my graph is coming down this way. But just to be sure, I might plot, let's say, -2, I might plot -1, and I even might plot one more value too. So at -2, now this is, let's just practice a little bit of algebra review here. If I have, 1/2, remember how in the previous slide we brought this down so that this power was positive? When I bring this back up, that actually becomes 2 to the -1 power. Because there's an x already there, that's times x. So really, it's 2 to the -x power. So when I plug in, of course, 0, right? When I plugged in 0 before, I got 2 to the 0 power, which is still 1. But when I plugged in 1, I actually got 2 to the negative 1 power, which, remember, is going to be 1 over 2 to the positive 1. But let's plug in negative 2 now. So if I plugged in 2 to the negative parenthesis negative 2 power, that's actually 2 to the second power, which is 4, positive 4. And then if I plug in negative 1, I'm going to go 2 to the negative parenthesis negative 1 power, and that's going to be 2 to the 1 power. So this is 2. Now I'm going to plug in 2, and I'm going to go 2 to the negative parenthesis 2 power. Well, 2 to the negative 2 power is just 2 to the negative 2. But remember that you're going to flip that over, and it's going to become 1 over 2 to the positive 2. Anytime you change levels with your exponents, it changes the sign of the power. So by going to the denominator, if it was a negative on the top, now it's going to be a positive on the bottom. And that's just going to be 1 over 4. So plotting those additional points, I've got negative 2, positive 4. I've got negative 1, 2. And it looks like I have 2 1/4, which therefore is carrying on my exponential equation. And again, don't forget that you do have a horizontal asymptote at y is equal to 0. And of course, that's just because there's no value here. That's my HA, this value right here. Here's just some examples of some exponential equations. You can look at these at leisure. That's fine. There are some properties of exponential equations that are actually really important. So we're going to go over those. Properties of exponential functions. Note that your b term, remember this, y equals a times b to the x power, this term has to be greater than 0, and it cannot equal 1. So that's really important that you do know that. It increases as b is greater than 1. It does decrease from 0 to 1. It is continuous. It is 1 to 1. Remember what 1 to 1 means is that it does pass the horizontal line test. The domain is all real numbers. The range does go from 0. Where's my range? Low value because let me see. I know you can't see all of that. The range does go from 0 to infinity. So meaning 0 because that's my asymptote right there. Let me erase this part. Okay. You also know that the horizontal asymptote is the y-axis, which is this. So that's y equals 0. You do have a y-intercept in every one of these at 0, 1. And you have an x-intercept of nothing because it doesn't cross the x-axis because you have an asymptote right there. Okay, so this is your increasing, and then let's bring this up. There's your decreasing. It has the same information as an exponential function. Here's some transformation summary, couple of things. Now, if you notice, these are different letters. Different textbooks use different letters, and I would not get comfortable with using any specific, like y equals a times b to the x. That's great to start with, to know what that does, but just know that different textbooks do use different variables. And so like I said, don't get caught up on, well, the A has to be in front. That's my y-intercept. Well, in this case right here, it's C, 0C is my y-intercept. Now, a couple of things too is in addition to C, this value in front is as being my, that value in front is being my y-intercept. It's also a vertical stretch or shrink. So basically it's, if it starts off like this, or actually like this, a vertical stretch would bring it up higher, and a shrink would be bringing it back down. In addition to that, if this value was negative, meaning it's less than 0, if the value in front of the equation, okay, let's say like negative 2 times 3 to the x power, this value right here would reflect the graph across the x-axis. Okay. In addition, let's see, we have the a term now, which is different because that was our b term. We just used a different letter. This value does have to be greater than 1, remember, but, excuse me, it has to be greater than 0, but it has to be less than 1. So it is a whole number or a fraction. It's a whole number if it's a growth, and it's a fraction if it's a decrease. Instead of a growth, it's not. So let's see here. This value in front, sometimes we have a value in front of the parentheses here. That's my horizontal stretch, okay? That's just going to widen it. In addition to that, if this value was negative, okay, if that value is negative, that would be a reflection across the y-axis. That's really important. This value here basically moves my equation to the left or to the right. And then the last value here is going to move it up and down. And sometimes if it's exponential, of course, that's also what we call my horizontal asymptote. Here's some applications of why you would use a exponential equation. And so let's practice this again. Going on the next slide. Now I've changed the letters. I need you to make sure that you know what these are without specific letters. So this value in front could be, if it's negative, it's a reflection across the x-axis. It's also a vertical stretch or shrink. This value here, remember, has to be greater than 0, but has to be less than 1. Also the a value, by the way, remember that's my y-intercept. This c value right here is a horizontal stretch or shrink. This value will move my graph to the right or to the left. If it's plus or minus, it'll move my graph right or left. This value here, if it's plus or minus, will move my graph up or down. Now at this point, I would definitely start experimenting with some of the with some graphs on, let's say, Desmos or on your calculator to start practicing. So let's get started on that. We're going to try a couple without a calculator, and then of course I would always go to the calculator to verify your values. And one of the things that I always remind students to do is to always start with what we call the parent graph. The parent graph is basically the graph without all the extra stuff. So like in this graph right here, my parent graph would be y equals, because remember, that's y. My parent graph would be y equals 2 to the x value. You've got your base, and then you've got your exponent. And remember, we actually did graph this, but just to remind you of what this looked like, I would plug in 0 and 1 for x because that's x. Now, if I plug in 0, I get 2 to the 0 power. Well, anything to the 0 power is 1. If I plug in 1, I get 2 to the 1 power, which is just 2. So graphing that, I have 0, 1, and I have 1, 2. And so I know this is exponential. I know this being an exponential equation that I do have certain properties that we just talked about 2 slides ago. And one of the properties is that my horizontal asymptote is at y equals 0. It also tells me that this is going to go up pretty quick like that. Now, a couple of things with this. This value here, see this plus 3? What that's going to do is it's going to take me 3 in the negative direction. This value right here is going to take me -4. And in an exponential equation, that value right here becomes my horizontal asymptote. So basically, if I wanted to bring this down already, 1, 2, 3, 4, I already know that my graph is going to be down here. The plus 3, I'm going to move this right here to the left 3. So you can either move your graph 3 units to the left, or you can take your point 0, 1 and move it to the left 3. And you can take your point, 1, 2, and then you can move it to the left 3. And in doing that, now my graph does this, okay? And in addition to that, I'm actually going to move it down 4, so I can take individual points and move them down 4, or I can just, I can actually just move my graph, which is kind of cool, but most of you are going to have to change the points, plot points. Keep in mind that these points here are not the points on my graph anymore. These were from my parent function, and my parent function is now not what my final graph is. But it doesn't mean that you can't actually plot points from your final graph. I do want you to practice that at some point, and do plug in 0, do plug in 1, but also plug in like -1 and -2 and maybe even 2. See, if I plugged in 0, I would have 2 to the 0 plus 3 power, so that's 2 to the third power. Well, what's 2 to the third? That's 2 times 2 times 2, which is 8. 8 minus 4 is 4, so 0, 4. So actually, this graph is coming up pretty high, and so my graph is a little bit off from that. Plugging in 1, I would get 2 to the 1 plus 3. Well, that's 2 to the fourth power, which is 16. 16 minus 4 is 12. So at 1, I'm actually way up here at 12, okay? If I plugged in -1, that would be 2 to the -1 plus 3. So that's 2 to the second power, which is 4. 4 minus 4 is 0. So at -1, I'm actually at 0. So it just kind of showed me that my graph is over a little bit. So these right here are actually the best points to plot your final graph, because that's actually where your final graph is. And if you just are kind of moving your graph along and without plotting points and without actually moving them, you're not going to be as accurate as you can be. And especially if on a test or a quiz, you're asked to plot, 4 points. These are not the points that you're going to graph. These are just your parent points to start you. These are the points right here that you're going to write down and give as final answer. Okay. So starting with this graph right here, I would start with my parent graph, which is 1 over 3 to the x power, and I would plot my 2 points, the favorite points, 0 and 1. So if I plug in 0, I get 1/3 to the 0 power, which is 1, and 1/3 to the 1 power is 1/3. So I've got so far 0, 1, and over 1, 1/3. Now keep in mind, this is a fraction. So that tells me that my graph is actually a decay. It is going to come down. I still have my asymptote going there. But this value tells me that that's my horizontal asymptote. So my horizontal asymptote is going to be moving up 4 units, okay? 2 things. Before you move anything, switch anything, do anything, you always want to do your reflections, because that's going to change the way your graph actually looks. So we have a negative sign in front. That means this value right here, that I'm going to reflect my graph across the x-axis. Okay, if it was a negative sign up here, that means I would reflect it across the y-axis, so it would be like that. But because it's across the x-axis, these values are now like this, and so my graph does look like that. Okay. And then +4 just means my graph is going to be picked up, and not that one. Okay, I lost my points. This graph right here is going to go up 4. And remember, that being my horizontal asymptote, because it was at 0, y equals 0, I'm moving it up 4. So my whole graph is going up 4. Now, this guy, his name's Leonardo Euler. I know it looks like Euler, but that's not how you say it. It's Euler. He discovered this really cool number E, letter E, but stands for a number, sort of like pi, which is 3.14. Euler came up with this 2.7, which has something, it is irrational, and it does show up all over the place, especially when we're using logarithms. So it does have some really cool annotations, and we're going to learn about the letter E. So just to get started, what I would do is to get a calculator. You guys should all have something like this. This is a TI 80. This is a TI Inspire CAS, which I think is the best calculator that I would buy for my kids. And you know, my students, actually, we did buy these for our students anyway. And plugging in e to the 1, e to the 0 power, keep in mind there is a button here that does say E right here. And so that actually is what you want to push. Okay, so when you're pushing that, that's E, says E to the X power. The X is going to be like an open box. And that just basically means that's where you put the 1. So when you plot those numbers, and you know, just take a minute and plot all of those: e to the 1, e to the 0, e to the -1, and e to the 0.5. And when you do that, you can stop the video and then start back up again, but you should practice and be able to plot these points in your calculator. So when you did that, you got these values here. What I want to talk about here is, you know, e just to the 1 power. I was telling you that e is 2.718. E to the 0 power is 1. And e to the -1, remember that's like one of our inverse, that's 1 over e, which is the same thing as saying 1 over 2.718, or 1 divided by that value is this value here, 3.3678. And then e to the 0.5 power, 0.5 is the same as saying e to the 1/2 power. And if you recall, what's a half power? I mean, you should know that a half power is the square root. And so that's really just saying, well, what's the square root of e? Because you remember the 1/2 is, this is the 1 here. There's a little 2 here. We don't see those when we talk about a square root, but we do know those are there. So anyway, that's basically saying, what's the square root of e? Well, this is my value here. Okay, so in addition to just plotting some that, or just to know what some of the values are, we're actually going to graph this. And notice that y equals e to the x. This graph of this equation, you remember what e is the same thing as really saying 2.718 to the x power. Well, 2.718 to the x power, remember, if we plot 0, what's anything to the 0 power? 1. And if we plug in 1, so that's e to the 1 power, well, that's 2.718. E to the -1 power is 1 over e, or 1 over, and we just got that value, is 0.3678. So that's this value right here, 3678. Okay, so in plotting those points, we have 0, 1. Again, it is exponential. It does have all of the properties that a regular exponential does have, including the horizontal asymptote at y equals 0. 1, 2.7. Now, this is a little bit different than the other graph. And the other graph that I'm talking about is the 2 to the x. Now, this is f of x equals e to the x power, this one. But remember, when we were just plotting a few minutes ago, we were plotting y equals 2 to the x. And what that's going to do, just keep in mind, is that's just a little bit wider. And the reason for that is when you plug in, 0, 1 and 1, 2, that value is a little bit lower because it is 2 instead of 2.17. Okay. Also, this value right here is asking for its inverse. See this negative sign here? That's saying reflect across the y-axis. That's what that's saying. So when I reflect that across the y-axis, now this graph, this point is here. This is still here. And remember, that's my y-axis. It is going to look like that. Okay. Oh, and that's it. So that should do it for today. We'll have more practice in the following lessons, and super important lesson for logarithms starting next session. So keep an eye out, and I hope that helped you with the graphs of exponential functions and graphing transformations. All right, thank you.